When it comes to learning about stars, there's no closer classroom than our sun. That's why NASA began an in-depth study of the Sun and Earth relationship in a program dubbed Living with a Star. The first mission in the Space Weather Program is the Solar Dynamics Observatory, or SDO, scheduled to launch from Cape Canaveral Air Force Station in Florida.
Welcome to the Solar Dynamics Observatory webcast. I'm Tiffany Now with NASA's Launch Services Program. In the next few minutes, we'll tell you what SDO might uncover about the Sun and how all of us on Earth can benefit from finding out more about that bright orange disk in the sky. But SDO is not NASA's first mission to study the Sun.
Several of NASA's past missions focused on the Sun. Pioneer 5 was the first. It launched in 1960 with instruments to study the solar wind and other phenomena. The instruments are primitive by today's standards, but back then, Pioneer gave researchers their first up-close look at a star. In 1973, NASA made observing the Sun a central goal of the Skylab space station. The agency's first space station included a telescope designed to look closely at the Sun. Astronauts living on the station spent hours making specialized observations.
What they found on Skylab was what we call coronal holes. And we did not know about coronal holes until they started taking these images. I would say that Skylab coming out with that type of photography was one of its most important things.
SDO's cutting-edge instruments offer researchers an unprecedented opportunity to examine the star at the center of our solar system. In fact, the readings are expected to be precise enough for researchers to forecast solar weather and predict when satellites in space and even electronics on Earth will be endangered by a storm on the Sun.
We had 15 years of fairly constant data stream, and we've taken that data and designed SDO to improve the ability to do science and to the ability to predict space weather. We measure not just the strength of the magnetic field, we measure also its direction. And we think that how much the magnetic field direction changes over a small part of the Sun is probably related to whether or not space weather things are going to happen.
Solar flares can cause power surges on Earth and wreak havoc on space stations and satellites orbiting the planet. So researchers want to find out what makes solar flares and other turbulent events occur on the Sun, and then find out if there's a pattern or signs that we could use on Earth to predict future flares.
SDO will look at the Sun and try to understand where the magnetic field comes from. When we talk about flares and coronal mass ejections, that's the Sun getting rid of stuff. That magnetic field is no longer in the Sun, it wants it gone. And it gets rid of the energy by having magnetic flares that release bright flashes of light, and it gets rid of the leftover magnetic field by just throwing it off.
The spacecraft will use 3 instruments to examine the Sun, including one that will take pictures rivaling the resolution of an IMAX movie. Another instrument, called the Helioseismic and Magnetic Imager, or HMI, will measure the sound waves bouncing around inside the Sun to construct an image of the star's inner workings. The data could reveal why the Sun operates in an 11-year cycle of activity. The Extreme Ultraviolet Variability experiment will monitor the Sun's brightness in the extreme ultraviolet wavelength, which changes constantly.
Our 3 instruments on here are really new and improved versions of some other instruments that have flown. And of course we have a lot more data and we take a lot more pictures. And that's one thing the scientists love, because as they say, the Sun changes all the time. It changes every second, and we're going to be imaging it every second, and we image the full disk of the Sun.
Taken together, the information SDO collects could give scientists ways to predict future solar disturbances and help developers on Earth come up with ways to protect sensitive electronics in space and on the planet. While the work from SDO is expected to be groundbreaking, it took a lot of researchers and several previous missions to show scientists what kind of instruments they would need to put on the spacecraft. Solar studies have relied on data from a host of missions looking at the Sun from different perspectives. The Solar Maximum mission launched in 1980 to look at solar flares and other events. The mission was extended by shuttle astronauts in 1984, who repaired the spacecraft in orbit. Solar Max operated until 1989. NASA and the European Space Agency jointly developed the Ulysses spacecraft, which launched on Shuttle Discovery in 1990. Ulysses gave researchers unique looks at the Sun's north and south poles. The Solar and Heliospheric Observatory, known as SOHO, launched in 1995 aboard an Atlas II. SOHO's observations are similar to those envisioned for SDO, although SDO is carrying more advanced instruments.
Well, the big challenge of this mission is its data rate. It's 150 megabits per second, 24 hours a day. It's relentless. Most of the astronomical spacecraft are looking at sort of faint sources, so they don't have that much light. We're looking at the sun, right? A lot of photons come off the sun, and we got to process those and get them down to the ground.
But before SDO can start its observations, it has to get into space. That's the job of a powerful Atlas V rocket. The Atlas will lift the 6,800-pound spacecraft to an orbit about 22,000 miles above Earth. The Atlas V is one of the largest boosters available to NASA and was used to launch the Lunar Reconnaissance Orbiter and moon-impacting L-Cross spacecraft.
SDO is one of the largest solar observatories we've ever launched. It had a heavy lift requirement, so we chose the Atlas V as the rocket for this mission.
The Atlas V is unique for its launch structure.
Atlas V has been a very reliable rocket. We've used it on a couple of NASA missions. It's unique in that it's chosen a clean pad concept for its launch processing. The rocket's actually built on a mobile launch platform in the vehicle behind me, the vertical integration facility, and then rolled out with rail cars out to the pad the day of launch. One advantage of this clean pad concept that they chose is that the rocket is processed safe and secure in a building, and then it rolls out the day of launch. And that way, if they have a problem, a storm or something like that, they can roll back into the facility. It's not exposed to the elements for very long. It just gives them a lot of flexibility in the processing and a lot of protection for the rocket as well as the spacecraft.
The day before launch, technicians will roll the rocket out of its protective service structure. They'll fuel the first stage and the Centaur upper stage as the Atlas stands on the pad. The spacecraft was built in Maryland at NASA's Goddard Space Flight Center, and it arrived in Florida in August 2009. It went through a number of comprehensive tests, including deploying the spacecraft's solar arrays. Technicians installed SDO's batteries and loaded fuel into the spacecraft before it was trucked to the launch complex. Spacecraft typically spend several months in launch integration and testing because the machines are designed to work in such a harsh place that technicians and scientists want to make sure everything is just right before launch.
The sun is our astrophysical laboratory. This is the place where we look at the sun and stop calling it the sun. When we look at the sun, it's just an average star. When we look out in the universe and we plot star stuff up, the sun's always right in the middle. It's like the perfect average star. And if our average star has solar activity, then we should see activity on other stars, and indeed we do.
You know, we need to know when a solar event is going to happen. Well, we can save a life.
A day before the Solar Dynamics Observatory begins its mission, the excitement is reaching a crescendo here at NASA's Kennedy Space Center. We hope you've enjoyed this look at the mission and found out a little more about our closest star, the Sun. Thanks for watching. For NASA's Launch Services program, I'm Tiffany Nail.